Okay. And so now, what about reporting average molecular weight now for these chains? So we touched on this in the previous video where we know that most samples that are made through industry or other laboratory exercises give a distribution in the length of chains in a sample or in a material. And so we want to try to now calculate the average of this using some equations. Okay, so we'll first just put a couple of thoughts here before showing the equations for this. We know that the final molecular weight is often controlled by the relative rates of some of the steps that we know for making the polymers. So that is, the overall final molecular weight can be controlled by controlling the rate of initiation, the rate of propagation, and the termination steps. If one can control these or tune them up appropriately, one can favor very high molecular weight where all chains are nearly the same length, or you can favor more low molecular weight where all chains are the same length, or random sizes to the chains with everything from short to high molecular weight in those more uncontrolled polymerization mechanisms. Okay, so the polymer engineer or chemist has quite a bit of opportunity to control molecular weight, and there's lots of examples in the literature to help with these ideas. And so at the end of the day, what we're interested in at this point is the average molecular weight and how we obtain that. And so this can be obtained by averaging masses with the fraction of times that they might appear. So this gives what's called a number average molecular weight. It's more respective of the population of the number of chains of one certain type. So down below, we clearly have one chain of this type and another chain of this type. If there were twins to each of these, then there would be two of each, etc. And that would be speaking to a number fraction ultimately. The 1 over the total of 2 that we see on screen would be the number fraction for the low molecular weight. And likewise, a 1 over total of 2 for the high molecular weight would be the number fraction there. So that's one idea that's built into the number average molecular weight approach. Or we can do something similar with a mass fraction, where we use that idea but instead weight it according to the mass of the chain. So we would take the mass of this chain multiplied by the number of the chains present and divide through by the overall mass of the sample. Okay, so whatever this mass value is would come in to here, and then we would divide through by the total mass of the sample to speak to the weight fraction or the weight average the weight fraction to help us calculate weight average molecular weight. Okay, we'll see that in an example in the next slide. Okay, so we'll see here that the number average molecular weight is given this equation. So it's molar mass number with a sub n, and we show the average symbol above. And we see that it is the sum of a feature called xi. So this is the number fraction of chains that are of a particular size range, I. Okay, so that might be a fractional amount between 0 and 1. The sum of all xi values might total 1. Okay, and so then that's going to be multiplying by the mass of that molecular weight size range of interest, so that I value again. Okay, weight average, we're going to have now the weight fraction instead or in place of the number fraction. So clearly how we describe the fractional amount of these chains is going to influence the difference between the number average and the weight average molecular weight of the sample. What we'll also see is that the weight average molecular weight value is always greater. It's always greater, you see here on the x-axis, always greater than the number average molecular weight outcome. And this is useful because we can characterize the breadth of the molecular weight distribution here by knowing just how far away the MW is and how much larger it is than MN. So we can do that by just simply looking at the two features. There's also a parameter called the polydispersity index. PDI. And this is the fraction of the two. We're going to put the larger number on top, so it is MW average divided by MN average. And this value is always going to be greater than 1, given that we know that MW is always larger than MN. And so the closer we are to 1, the closer that this value is to MN. The more narrow the molecular weight distribution, the more alike the chain lengths are, and overall their molecular weight. Okay, so this is an important way also to characterize the molecular weight distribution that exists in a sample. Okay, so let's look at an example calculation using data that might be familiar to you. So here's an arbitrary student set of data where students kind of numbered, if you want, 1 through 10 are found, and their weight in pounds is listed down the chart. Okay, so we can ask the question, what is the average weight of students in the class? And so you might be automatically thinking that, to simply take the sum of the weight of all students and divide it through by the total number of students, that is 10. What you would be doing there is calculating a number average result there. So you're speaking to the approach for A, but we would need to develop other ideas here to speak to the approach for the weight average, and so we'll see that. To develop those approaches, what we're going to do is develop what we listed earlier, the ideas of a number fraction and a weight fraction to help us with this. Okay, so let's look at this data and see if we can eventually build up the concepts for number average and weight average estimates for the classroom, and then eventually apply that to a polymer. Okay, so the first thing we're going to do is we're going to bin the data a little bit. So we're going to sort the student data into weight ranges. Okay, so those 10 students now have some of their weight information represented by only one row in this table. Okay, so you'll see here the number of students and I that contribute to the mass range between 81 and 120 is 2. Okay, and an additional 2 other students contribute to the next mass range. Okay, so we've binned the next range between 121 and 160 pounds. Okay, so we had 10 students, so we've already binned up 4 of them in total now. There's 3 more that fall into the next category, 161 to 200, then the next category, 201 to 240, and that gives us all but the final student, and we have the final student's mass information down here. Okay, so hopefully that piece of the approach is straightforward to you. We've provided some binning now, speaking to what might look like a bar chart here for the ultimate population of students of certain mass versus that mass as a chart. Okay, and so what we want to get now is this number fraction information. Okay, so we're going to use this value now, the NI values, to help us with that, and we're going to use the information for the bin that we had. So the mean weight of the bin, that is the average between the limits here, is 110 pounds. Okay, so if we take the average of 81 and 120, we'll end up with 110 pounds there. Okay, likewise for the next bin, the average there is going to be 140. And likewise for the next bin, 184, etc. Okay, so to show how we get the first number fraction, what we're going to do is take the number of students involved and divide it through by the total number of students. Okay, so for the first row, what do we have? We have X for the bin of interest, the first one. The number fraction is going to represent the 2 students divided through by the total of students is 10. So the number fraction is of course 0.2. Okay. You could imagine doing this for all of the data. So for example, This calculation isn't overly involved, so if we were to put the xi values down the column here, we saw that the first one was going to be 0.2. The next one I'm going to have 2 divided by the total number of students. That's going to be 10 again, so that's going to be the 0.2. The next entry, I have 3 students contributing there, and I have still the same number of total students, so that's going to be a 0.3 value. I then return to 0.2 in the next entry, then I have 0, 0, 0, and then I have a final value of 0.1. So notice here that the sum of xi is, of course, 1. We've now normalized all the data to sum to a total of 1 by using a number fraction rather than an explicit number for the number of students involved in this data set. This is useful because it puts all data between a 0 and 1 value instead of an arbitrary class that may not have 10 students. It may have 41 students or some other arbitrary number. Okay, so hopefully this is straightforward to you. Now, the weight fraction information is subtly different. We're going to see that for the first row of information, we're going to evolve the numerator to now have a weighted value according to the weight of the student. Okay, so let's just make some room for that information. Okay. So what does the weight fraction of a row look like in this case? So the weight fraction of the first row of information here, we're going to take the total number of students. I see that again, 2. Okay. And let me just sort of clean this up so it's very clear. And we're going to multiply now by the mass of that row. So the average mass of that row was 110. We saw that a moment ago. And as we said earlier, we're going to divide this now not by the number of students, but the total mass of the sample. So the total mass of the sample in this case is the weight total for the class. So it is the sum of all of this. Okay, so that is going to equal the 1881, I think it was, down here. So it is the total weight. Okay, so in a sense, it's the sum of the products of the two columns that we see in our table. Okay, so for the first xi value, we have 2 times 110 divided through by the sum of the whole class. Okay, and so that's going to give us this first value of 0.117. Okay, so these are not as easy to predict because we have clearly a different denominator here than the simple 10 that we had before. Okay, so that's our first weight fraction information, 0.117. Okay, so to just kind of clean things up, I've got this already on the next slide. So we saw a moment ago that the number of students, Ni, was 2 in the first category, 2 in the second category, 3 in the third category, 2 in the third category, 0, 0, 0, and 1 in the final category. And hopefully you saw how Ni becomes Xi through a simple population analysis. 2 divided by 10, 2 divided by 10, 3 divided by 10, etc. And the sum of that equals the 1. So the sum of all xi values equals 1. Now, when we look at weight fraction, we did a calculation a moment ago for this. So that green boxed feature, we saw that calculation earlier on the previous slide. The next entry is going to be 0.15. So the approach there was to take the total number of students times the weight of that bin divided through the total. Okay, so to get the next one, we would take 2 times the mass of average of that bin, so that's going to be the 142 divided through by the total, so that's the 1881, and that gives you that fraction. Okay, and so the pattern continues down. When we have no students, so when the value of 2 is 0, we have no entries there, and then we have a final value of 0.202 from the last student. Okay, so these are our xi and wi values. What is the use of that? these, as we see, are going to come into our coefficients needed for summing to get us the number average molecular weight, or the weight average molecular weight. Okay, so let's look at that. We have the number between 0 and 1 times the mass of that bin, and that is going to get added to the next fractional amount of the next weight of the bin and the next weight, and that's going to be the simple approach to getting the number average. Now that we have the WI values, you can see how the equation is going to look similar. So with those ideas, let's go back and let's look at the calculation for the number average molecular mass of the students in this class. Okay, so we saw the 0.2, that was our red square up there. Okay, so this red square here, we see that value right here, and we're going to multiply through by the weight of the average weight of the row. So here it is right there. So there's our first feature that needs to get summed against all the other features that are in similar pattern, where we take the xi value times the average weight of the bin. Okay, so here we see that the number of entries in our table is 4 plus the 1, so I should have 5 features that have to get summed up, and we see those reflected in the first row. Okay, so in the last one all the way down, maybe focusing over here, we can see that the xi value of only 0.1 multiplied by the 380 is our final feature, and of course that gets summed with all the other ones along the way. And finally we get the number average weight of students in this class to be 188. And this is a long way to get the exact same thing if you had summed the mass and divided through by the number of students. Right? We saw a moment ago that the total mass of the students was 1881 divided by 10, and that of course gives us this number. Okay. Now, perhaps of more value is the logic here for getting weight average molecular weight. So here's where we use the weight fraction information. Okay, so we're going to do a similar thing. We're going to take now that weight fraction information. We saw how to get the green box a moment ago. We're going to multiply it through by the average of the bin, and that's going to be our first feature there. Our next feature, same pattern, multiply together, and then we have the fifth down here. And so again, bed mass, we would multiply these two together, then finally sum the 5 components together. And notice that we get a final value here that's 218 pounds, quite a bit different than what you would have had. And notice that the weighted average value for the student in the class is higher than the number average value. It fits with the idea that MW average is greater than MN, as we saw when we defined the polydispersity index equation. Okay, so if you can handle all that, I think you're ready for molecular weight